Yeah. So in this P channel, uh, so actually N channel transfer characteristics, how did you get? And for like this we got. So like this we got. So because VGS is negative there in P channel, but in the N channel, but in P channel, so VGS is a positive value. VGS is positive value, so that is coming from the first quadrant here. So this is the positive VGS ID, and the graph will be in the first quadrant. But N channel VGS is negative, ID is positive, so that will come in the second quadrant. Okay, so here the coming to the drain characteristics, and for that the drain characteristics, how did you get this is 0 here. Okay, so now see, and this is what so VGS equal this is N channel, so N channel, so how did you get here? Okay, so 0 volts. Okay, so now it is 0 volts, let us say. Suppose now we are applying the VGS is equal to positive. We are applying the VGS equal to positive. If VGS is equal to positive apply, so this becomes a reverse bias. This depletion region becomes widens, so the depletion region will enter into the channel, so that the length of the channel becomes small. So therefore the current also becomes small. Okay, so this is the 1, this is the 2, and this is the 3, and so on. So like this, you see 0 volts, 1 volt, 2 volt, 3 volt, 4 volt. Okay, so if you understand the operation of N channel, it is very easy to understand the operation of P channel. So just quite opposite to N channel. So for N channel, you have the 2 years. For P channel, you are applying the positive VGS. Okay, so the remaining is same, that operation, but there the electrons flows, but here holes flows. Okay, so there the current flows from drain to source, but here the current flows from drain to source to drain. Okay, so that just try to understand the operation, and if you have any queries, we'll discuss in the next class this one P channel. So this is the symbol of this one. Okay, this is the symbol of P channel. Please note down this characteristic symbol, and we'll move to the next topic. Is it over? Over?
Yes, sir.
So next, take the heading the characteristics characteristic parameters of JFET. So from the transfer and drain characteristics, what are the parameters that we can calculate? There are the three important parameters. So one is a mutual conductance or transconductance indicated by letter GM, the drain resistance RD, amplification factor mu. Okay, so mutual conductance or transconductance. So you know that. So transconductance is nothing but the current, output current by input voltage. So what will be that output current? Okay, what will so transconductance is output current by input voltage. So output current is ID here. Input voltage is VGS. So it is the slope of transfer characteristic curve and is defined by GM is equal to dou ID by dou VGS at VGS is constant. Okay, that indicated with GM. The drain resistance RD. Drain resistance RD, where did you get? And we will get this RD from output characteristics. So output voltage and so resistance means current by voltage by current. We know that according to the Ohm's law. So it is a reciprocal of slope of the drain characteristics, and it is defined as dou VDS by dou ID. That is RD. And finally, amplification factor mu, it is defined by so mu is equal to minus of output voltage by input voltage. So dou VDS by dou VGS. These are the three important parameters. Like if we take the BJT characteristics, we have H parameters, no? So like so HI, HF, HR, HOE. So like that. So these are the parameters for the JFET. These are the parameters for the JFET. So like H parameters of BJT. Mutual conductance, drain resistance, amplification factor. Okay, so next the relationship among effect parameters are like this. So using Taylor series we can express. So as ID is a function of EDS comma VGS. So ID is a function of that, we can write it as ID equal to is a function of VGS comma VDS. Okay, so means so ID depends on both the input voltage and output voltage. Okay, that using that as a Taylor series we can expand the equation like this. So dou ID is equal to so delta ID is equal to dou ID by dou VDS into delta VDS, okay, plus dou ID by dou VGS into delta VGS. So using that Taylor series we can expand the equation like this. Okay, and so now take the common part. So if you take the VDS, delta VDS as common, so delta VDS if you take common, so that you can write as delta VD by delta VDS equal to, so dou ID by dou VDS. Okay, second ID by this is VGS, not VDS, VGS. If you take VGS as common, delta ID by delta VGS, So that you can write it from this term, you are taking the common. So dou id by dou vgs is a single parameter. Then so dou id by dou vds into delta vds by delta vgs. Okay, but if id is constant, so because if you take the characteristic at a pinch of region current, if you take the characteristic of a drain characteristic like this, so the current will be constant like this. It maintains the constant in the pinch of region like this. So there is no change. So the delta, the current is constant, the delta id becomes 0. So the delta id by delta vg is equal to 0 here. The delta is 0 here. Okay, so now this part, so this you can simply you can use you make it 0, that equal to dou id by dou vds. Actually dou vds by dou id is rd, but now so current by voltage means I can write it as 1 by rd into vds by vgs. Okay, vds by vgs is minus mu. Okay, according to the definitions, id by vgs, id by vgs is gm. Okay, now you can rewrite the equation. You will get mu is equal to gm into rd. You can rewrite the equation. So this is the relation between the characteristic parameters of JFET. Mu is equal to gm into rd. So that equation, and the expression for saturation drain current is given by, so there is no derivation part and the proof for this equation, but this is a fixed equation. IDS is equal to IDSS into 1 minus VGS by VP whole square. Okay, this is only one and only equation in the third module. So if the question comes in any numericals, that numerical problem will be based on this formula only. Only one problem, one equation in this entire third module. The JFET and MOSFET along together. IDS is equal to IDSS into 1 minus VGS by VP whole square, where IDSS is nothing but the maximum drain current at VGS is equal to 0. IDSS is the value of IDS when VGS is equal to 0. That is the maximum current. VGS anyway you know that is the gate to source voltage. VP is the pinch off voltage. VG is the pinch off voltage. Can anyone tell what is the pinch off voltage? What is pinch off voltage? C5. C5. What is pinch off voltage? Huh?
As VDS is increases at a certain value, VP of VDS, the cross-sectional area of the channel becomes minimum. At this voltage, the channel is said to be pinched off, and the voltage is known as pinch off voltage.
Okay, as in the drain characteristics, as VDS is keep on increasing, ID also increases. But at a particular time, as VDS is increases, the channel, the depletion regions of both sides, okay, will come closer, and the channel becomes very thin. And at a particular voltage, the channel will be closed, and that whatever the previous current is there, that will be maintained constant. Okay, so the voltage required to make a contact of these two depletion region is called the pinch off voltage, and that region will called as the pinch off region. Okay, so that is VP, and the expression for saturation drain current is given by, so this is the formula. And so please note down the comparison of JFET and BZT. So anyway, wantedly or by mistakenly, if you exit the class, that's it. You are not allowed to enter the class again. So in the last class, I already told. So by the next class, I told that, and lobby will be created, and those who joined before 10:35 only I will allow. So stick on that statement. Okay, I think so. So 5 members are waiting in the lobby. Over. Can anyone respond? It's over.
Yes, sir.
Okay. Now take the heading, next one. MOSFET. Next heading, MOSFET. So the first one is, let us discuss enhancement MOSFET. Enhancement MOSFET. So the JFET is over. The next topic we are moving to the MOSFET. Okay, so what is the another name for the MOSFET? What is another name for MOSFET? Yeah, IGFET, metal oxide semiconductor field effect transistor or insulated gated field effect transistor. MOSFET or enhancement, MOSFET or IGFET. So another name for this enhancement MOSFET is, you can call it as eMOSFET. Enhancement MOSFET or eMOSFET. Okay. So, so now let us see the construction first. Construction. Okay. So please note down the points what here I'm typing here. The N-channel MOSFET consists of a lightly doped P-type substrate which heavily doped, okay, N regions plus regions are diffused. Okay, so the first point is the N-channel MOSFET consists of heavily lightly doped P-type substrate into which now substrate, so in which two heavily doped and N plus regions are diffuse. So for example, so now we are discussing the construction of MOSFET. Okay, so this is same as for the depletion also. This is one substrate. So substrate means here we are discussing about the N channel now, so especially. Okay, so N channel. So this is let us take N channel enhancement MOSFET. Okay, so if you take N channel enhancement MOSFET, so we'll take the P type substrate. So the body's P type substrate is nothing but P type semiconductor will take. So this is P substrate. Okay, so this is just a basical one semiconductor. Okay, first we'll take N channel and MOSFET consists of a lightly doped P type substrate into which two heavily doped N plus regions are diffuse. So in this P substrate, two N plus regions are diffuse. These two N plus regions are the heavily doped N plus N type regions. Okay, so this is N plus here. Okay, so this is another N plus. Okay, so these N plus and N plus. So one P sub we are taking one P substrate. In that P substrate, we are diffusing two N regions. Okay, into the P substrate. So that is the first point. And the second point is, hello. Hello. Okay, N channel enhancement MOSFET or in MOSFET. So first we are taking a P type substrate. Suppose if you are taking N channel MOSFET means we have to take P substrate. Suppose if you take P channel enhancement MOSFET, you have to take N substrate, opposite. Okay, so if you take N substrate, so P regions will be diffused. Okay, please understand this. We are discussing about N channel enhancement MOSFET. In this N channel enhancement MOSFET, first we will take the substrate. So what type of substrate we have to take? Opposite polarity of that channel. So now the channel is N type, so substrate should be opposite, that is p type. So I'm taking p substrate first, then I am diffusing two n plus regions into the substrate. So like this. Okay, the next point is, okay, so this is the first point. Okay, the next point is these n plus regions, okay, which will act as the source and the drain. Source and drain are separated by about 1 mil. Sorry, 1 mil. Okay, so are separated by 1 mil here. Right, so 1 mil. So the distance between 1 mil. So come here, the distance. So these two terminals we are naming it as, this is the source and this is the drain. So this is the source terminal here and this is the drain terminal. So two n plus regions we are diffusing in p substrate. So those two are the source and drain. The distance between these source and drain is the what they are saying, that is 1 mil. 1 mil. Okay, so 1 mil is equal to what, you can you can convert, right, the conversion. 1 mil equal to, okay, 1000 part of 1 inch, so means 0.01, sorry, 0.1 inch. Okay, so 1 by 1000, 1 by 1000 part of inch, so 1 mil equal to 0.001 inch, that equal to, you can write 0.0254 millimeters. Right, so this is the distance between we should maintain with this distance we should maintain. So we should we diffuse that source and drain in the p substrate. We should diffuse source and drain in p substrate by maintaining the distance of 0.0254 millimeters. 0.0254 millimeters. Okay, so this is done. The next one, this is the second point. This is the second point here, and this is the first point, and this is the second point. Okay, so the third point is a thin layer of insulating silicon dioxide in bracket, I can write as SiO2, silicon dioxide, is grown over the surface of the entire structure, and holes are cut into the oxide layer, allowing surface, so allowing contact cuts for source and drain. So now what you're doing, so the third step is a thin layer of insulated silicon dioxide, so SiO2, is grown over the surface, the entire structure, and the holes are cut into the oxide layer, allowing contact cuts for the silica source and drain. So means in this over the surface we are placing in this surface we are placing one silicon dioxide. What is this? This is SiO2, silicon dioxide. Okay, and some holes are cut into the oxide layer, allowing contact cuts for source. So means here we'll apply some technique and we'll make one cut. So means this will be removed. Okay, so this will be removed, and here also one space cut. So like this. So what you can write. What you can write, this is the cuts is nothing but to make a contact for the source and drain. So we are providing some space, and here we'll insert to the lids. So that is the contact lids. Okay, that will see in the next step. So contact lids will insert here. So finally, this structure, how we can write it is, so from here to here, here to here, here to here. So this is the space we are providing, and we are removing some portion on source and drain terminals. Okay, to make a contact for these source and drain, and to take the connections out. Okay, so later, so this is the third step, and we are doing like this. And the fourth step is, okay, then the gate metal area is overlaid. Please, so then the gate metal area is overlaid on the oxide, covering the entire channel region. Okay. So then the gate metal is overlaid. Area is overlaid on the X side, covering the entire channel region. So from this, what you can write, this step, some metal, so that is what, I'm taking some other color, some gate. This is the gate area. Okay, so here we are connecting metal. Okay, so this will be gate terminal. This is the source terminal. This is gate terminal. Okay, finally the cuts will apply. That metal cuts will apply here over this, and one lid will come out. So this is the source. Similarly, gate also, one lid will come out, that is gate, and here also one lid will come out, this is drain. So this is the enhancement MOSFET, N-channel enhancement MOSFET, and you can observe one point here. You can observe one point in this. There is no connection between source and drain. There is no connection between okay, so there is no connection, there is no channel at all. Okay, so please keep it in mind, and there is no channel between the source and drain. So finally, this is the structure of N-channel enhancement MOSFET. Okay. Okay, so now coming to the point. So once the structure is over, so coming to here. Okay, so now see, okay, anyway, so what is the source? The source has to emit the charge carriers. The drain, it has to collect the charge carriers. That is fixed. Okay, the gate is what we will apply. So let us see here. The P substrate, what is the majority charge carriers? The majority charge carriers are the holes. So the positive. Okay, so this is the majority charge carriers here. Okay, so in these majority charge carriers, there are some minority charge carriers called electrons, like this, negative. Okay, there are the minority charge carriers, electrons, some minority charge carriers. So in order to push, so what is this source and drain? So both are N plus regions. N plus regions means what are the majority charge carriers here? Here the electrons are the majority charge carriers. So electrons from source has to travel from source to drain. So to travel that source to drain, so there is no path between the source to drain. There is no path. So if any path is there, then automatically that electron can flow. Okay, but for that, but according to the construction of N-channel enhancement MOSFET, so there is no physical channel. For that, what we have to do is we have to create manual channel between the source to drain. Okay, we have to create so artificial or manual channel, so that the electrons can flows from the source to drain easily. Okay, so how you can maintain, how you can create the channel? So there are the two possibilities. So the channel is, since both the source and the drain are n-type semiconductor charge carrier, n-type semiconductors, so majority charge carriers are electrons. So we have to attract. So we have to attract all the minority charge carriers in P substrate. Okay, so over, and you have to attract, and those will come and place near to the this oxide layer. So then if you attract these minority charge carriers, so those will come and place near to the oxide layer. Then this is a negative, and the channel is negative, and this is also negative. So finally the electrons can easily flows from source to drain. Okay, so to attract that minority charge carriers from the P substrate, what should be the gate voltage we have to apply? What should be the gate voltage that we have to apply to attract the electrons? Okay, what should be the supply we should apply? So here we need to attract the negative polarities. So the electrons we have to attract. So for that the gate voltage should be what? Is it positive voltage or negative voltage?
Positive.
Yeah, we should apply the positive voltage. So then only it will attract that negative charge particles. Okay, and meanwhile, so this is oxide. Okay, so this is oxide layer. Okay, so what is this? This is a semiconductor. The P substrate is nothing but what? So semiconductor. Okay, so what is this? This is called metal. Okay, metal. So if you see metal oxide semiconductor, so this is the reason it is named as a MOS means metal oxide semiconductors. Metal oxide semiconductor. Okay, so this is the layer. So you take this part separately. So this is the just it will come like this. So this is semiconductor, this is metal, this is oxide. Okay, so now you see the symbol. It is looking like the capacitors, right? The parallel, so the two parallel plates are there. It is looking like the capacitor. What is the behavior of the capacitor? If you apply positive polarity of one particular plate, okay, the opposite polarity will be diffused or induced in the opposite plate. Okay, so means if you take one parallel plates here, and if you apply the positive and positive here, so it will diffuse the opposite polarity to the opposite. So this will be the negative. Okay, if you apply the positive here, then it will release the negative here. So this is, we call it as inversion layer. Inversion layer means you are giving positive but you are getting negative. It will call the inversion layer or insulated layer. Insulator layer. So this is also looking like the capacitor. So you are applying the positive, and but here you are attracting the negative, so it acts as a that is parallel capacitor. So that is the MOS, metal oxide semiconductor. Okay, so another name is what? What is another name for the MOSFET? IGFET, insulated gate field effect transistor. What is insulated? Insulated is nothing but that inversion layer, that insulated. Okay, so likewise, so you will get we have to create a manual channel. We have to create a manual channel. So then only the electrons from source can travel to the drain. Okay, so that you have to do extra, and the remaining part is everything same what you studied in the JFET. What you studied in the JFET, so the remaining part is as usual. Okay, so now is it clear now? Any doubts in this?
Sir, what is the inversion layer, sir?
Inversion layer is nothing but you are applying the positive, but you are getting the negative. So this is the oxide layer, right? So here what you are getting, what you are applying, the positive polarities you are applying here onto the one plate. Positive apply చేస్తున్నారు మీరు. But in the next side plate మీకు ఏమొస్తుంది మీకు, it is attracting then minority charge cards in the P type. So but ఇక్కడ మీకు negative వస్తుంది మీకు. Okay, so actually it is looking like the parallel capacitor. So one parallel capacitor means ఒక ప్లేట్ కి వచ్చే మీ పాజిటివ్ పొలారిటీ అప్లై చేస్తే ఆపోజిట్ ప్లేట్ లో వచ్చేసి ఆపోజిట్ పొలారిటీ మీకు డిఫ్యూజ్ అవుతుంది, రైట్? సో బేస్డ్ ఆన్ దిస్ ఆపరేషన్, సో మీరు పాజిటివ్ ఇవ్వడం వల్ల ఏమవుతుంది, సెకండ్ సైడ్ వచ్చేసి నెగిటివ్ వచ్చేసి అట్రాక్ట్ అయిపోయి మీకు ఛానల్లో ప్లేస్ అవుతుంది. సో వెన్ ఎవర్ ద ఎలక్ట్రాన్స్ are attracting, sorry, the electrons are attracting towards the dioxide, silicon dioxide, and it is placed over between two n plus regions. Okay, but at the gate you are applying the positive, but you are getting the negative here, so which we call it as the inversion layer. Inversion is nothing but if you apply the negative, you will get positive. If you apply the positive, you will get negative, like that. Okay, even you can apply the negative, but what happens if you apply the negative, it will gives positive. So if you got positive comes and placed here, so these electrons, whatever the flowing from source to drain, it will participate in the covalent bond and it will not generate any kind of the electricity. So for that reason, we should attract electrons only in between the source and drain. So to attract the electrons, we have to apply the positive terminal battery. Okay, so you are applying the positive, but you are getting the negative, so it is a inversion layer. It's clear?
Yes, sir.
So this is the just construction. Now let us come into the operation of it. Okay, so operation. Okay, so now see the operation of this. So again the same steps what you had discussed in JFET. Let us see first one. Vgs equal to 0. Okay, Vds equal to 0. What happens? Vgs equal to 0, Vds equal to 0. What happens? So here, if you apply the Vgs is equal to 0, no channel exists, right? Yes or no? If you apply the Vgs is equal to 0, so you are not applying any input signal. You are not applying any input signal. You are making 0. How the channel can be created? If you apply the positive voltage, then only the channel can be created. Then you can apply, depends on the output voltage, so the electrons can flow. Yes or no?
Yes, sir.
Okay, so no channel exists. If the no channel exists, then what happens? ID current becomes
0.
Because there is no channel, so there is no path, so electron cannot travel from the source to drain. The current will be 0. Is it clear? So suppose if we take the second condition. Okay. So what is the second condition? So I'm taking Vgs equal to Vgs is increased from 0. Okay, increase from 0. Okay, and let us say again Vds equal to 0. The first step is both voltages are zeros, both input and output are zeros. The second step is input is increased from 0, but output is maintaining 0 again. Now what happened? What happened now? What happened? Is channel created? Yes or no? Is the channel created or not? If you apply Vgs increase from 0. Are you there in the class? Yeah, you are there, no? C1?
Sir.
Now tell me, so if you apply Vgs increase from 0, so means Vgs is positive. So what about the channel? Is it exist or not exist?
Not exist, sir.
Not exist. Okay. So then when it will exist? To create a channel, to exist a channel, what should we do then?
VDS increased from 0.
Okay.
VDS is not 0.
So to create a channel, so VDS should be increased from 0, right? Varun?
Sir.
What we have to do to create a channel?
VDS should be
VGS equal to 0 and VDS increased from 0.
VGS should be 0 and VDS should be increased from 0, na? You see here the channel, you see the circuit and tell me what we have to do for creating the channel. See the circuit and tell me. Say if we increase the VGS from 0, so means you are applying the positive voltage. If you are applying the positive voltage, automatically it will attract the minority charge carriers from the substrate, and so it will apply the inversion, so opposite polarity on the opposite places. So positive place, the negative charge carriers will place in the between the source and drain. Whenever we are applying the positive voltage for VGS, whenever you are applying positive voltage for VGS, so that is so from here to here, positive voltage from VGS, then the channel exists. తర్వాత కరెంట్ ఫ్లో అవుతుందా లేదా అనేది నెక్స్ట్ క్వశ్చన్. కరెంట్ జనరేట్ అవుతుందా లేదా అనేది దట్ డిపెండ్స్ ఆన్ VDS. ఓకే, సో ద కరెంట్ వచ్చేసి మీకు ఇట్ డిపెండ్స్ ఆన్ ద టూ థింగ్స్ నౌ. వన్ ఈజ్ వెదర్ ద ఛానల్ ఈస్ క్రియేటెడ్ ఆర్ నాట్. ఓకే, సో the second thing is whether the output voltage is increased or not. Both the points we have to take it. If you apply VGS is positive voltage, so what it will do, you are applying the positive you are applying, and the opposite polarity, so positive opposite negative will be diffused or induced in the opposite plate and at the same or you can tell that it will attract the minority charge carriers in p substrate. So all the electrons come and placed over between source and drain. So whenever the VGS is a positive applied, the channel will be created, there is no question. But whether the current generated or not, that depends on output voltage. So here, when the EGS is increased from 0, yes, channel exists. Okay, but now ID becomes again 0. Why? Because you are not applying output voltage. You are not so now what you are doing, you are creating a channel. You just create a channel, so the electrons are ready. So electrons are ready, or now it is capable of, it can travel from source to drain. It is ready. The electrons all are ready, but you are not applying the output voltage. So that is VDS. So that voltage will not attract the electrons from source to drain. Why? Because you are not applying. So because of that, the ID current becomes 0. Is that right? Okay, so simply, so in the simple statement I can write it as, when VGS increases 0, electrons attracts towards surface. That is one. Next, holes anyway repel and goes away. That anyway, so because you're applying the positive, so holes repel and goes away, and channel is created, and the ID current becomes 0. Why? Because you are not applying the output voltage. And the next third point is now VGS increase from 0 and VDS also increase from 0. Okay, so now tell me what happens. What happens? Is channel exist?
Yes, sir.
Yes.
Yes, sir.
Channel exist. What about current? Same. If channel exist means the electrons are attract towards surface, holes repel, goes away, and the channel exists. It means same means. Now coming to the ID current. What about ID?
Not equal to 0.
So ID enhance by VGS and VDS. Enhance means it will increase. Enhance means it will increase by VDS and VGS. So if VGS keep on increasing, VDS is keep on increasing, automatically the current will increase. So the current is increasing, enhancing by VGS and VDS. So both are positive directionally. So VGS is positive and VDS is also positive. So hence this named as enhancement MOSFET. Hence it is named as enhancement MOSFET. So ID is the function of ID is the function of VGS comma VDS. As VGS increases, the conductivity of the channel increases, and thereby current drain current increases. Okay, so hence it is named as this enhancement MOSFET, or in shortcut we can call it as E MOSFET. In shortcut we can call it as E MOSFET. Okay, so see, this is what I am telling you, so that everything is in the words you can explain, you can write on your own words. That's not an issue. So only thing is we have to write the conditions, like if VGS equal 0, VDS equal 0, what happens? You have to write a statements. And the next point, if VGS is increased 0 and VDS maintaining 0, what happens? You have to write in terms of statements. And the third point, if VGS increased from 0, VDS also increased from 0, what happens? You have to write in terms of your words or your sentences. So that's enough. This is, see, they need not to prepare and need not to add anything. Only thing is, you please keep it in mind, the source should be repel, so that it has to emit the charge carrier, drain has to collect the charge carrier. That only you keep it in mind. That only, please keep it in your mind, that only. Okay, in this enhancement MOSFET, n channel enhancement MOSFET, gate always positive. You are not supposed to apply the negative voltage here. Okay, enhancement MOSFET lo gate anedi positive ne, eppudu positive ne. If you apply the negative, the channel will not create, so ID current 0, it becomes 0. Okay, so gate voltage always positive for n channel E MOSFET. For P channel E MOSFET ki gate voltage enti? For P channel enhancement MOSFET, what will be the gate voltage? Negative. So for that is negative. Okay, so please understand, to create the channel what we have to apply, that's only the point. So మీకు రెండు, సో సబ్స్ట్రేట్ మీకు ఛానల్ క్రియేట్ అవ్వాలంటే, సో మీకు డిఫ్యూషన్స్ ఏమున్నాయి? ఎన్ టైప్ ఉంది. సో రెండు ఎన్ టైప్ కాబట్టి మధ్యలో మీకు ఎలక్ట్రాన్స్ రావాలంటే పైన పాజిటివ్ అప్లై చేయాలి. లేదు టూ సైడ్స్ మీకు పాజిటివ్ అంటే పీ టైప్ ఉన్నాయి, పీ టైప్ రీజియన్ డిఫ్యూషన్స్. సో మీకు మధ్యలో ఛానల్కి హోల్స్ కావాలి, అప్పుడే మీకు ట్రావెల్ అవుతుంది. సో మీకు హోల్స్ మీకు ఇక్కడ రావాలంటే పైన మీరు నెగిటివ్ అప్లై చేయాలి, దట్ ఈస్ పీ టైప్, పీ ఛానల్. Okay, so based on that, please understand. So these three conditions you can apply. Okay, so conditions, and you can note down the points. Is it clear? Any doubts in this?
Sir?
Yeah.
Holes will be repelled.
Second.
How holes will be repelled?
You are applying the positive, no? So here you are applying the positive right here. Okay, so these positive polarity will attract the electrons and repel the holes. So gate ki meer positive voltage apply chestunaru kadamma. Yes or no? Gate ki positive apply chestappudu it attracts only the electrons. The positive, మీ పాజిటివ్ బ్యాటరీ ఇస్తున్నారంటే ఏంటి? సపోజ్ ఒక పీ టైప్ సెమీ కండక్టర్ ఉంది, ఇది పీ టైప్ సెమీ కండక్టర్ ఉంది దీనికి. ఓకే నెగిటివ్ ఇస్తే ఏమవుతుంది హోల్స్ అన్ని ఇటు వస్తాయి అదే పాజిటివ్ ఇస్తే ఏమవుతుంది హోల్స్ అన్ని ఇట్ గోస్ అవే ఫ్రమ్ ది దట్ పాయింట్ right so same point you are giving the positive voltage for the gate you are applying the positive voltage for gate okay and so it will the gate positive istunarante meeku opposite negative attracts so it attracts the negative and repels the positive the gate voltage is positive it attracts the negative and repels the positive so that is the reason electrons are attracted and holes are repelled clear
Yes, sir.
okay so now coming to the characteristics now let us draw the characteristics so based on this static characteristics so the first point is so what we can write id is a function of we know that vgs comma vds id is a function of vgs comma vds so first characteristics what you can write vgs versus id okay so this will called as so by keeping VDS constant okay so these characteristics we call it as a transfer characteristic curve transfer characteristic curve second point is VDS versus ID so again by keeping VGS is constant these will called as drain characteristics okay static characteristics id is a function of f of vgs comma vds first characteristics will draw vgs versus id by keeping vds constant that will call it as transfer characteristic curve second characteristic is id vds versus id vds output voltage versus output current by keeping vgs constant that will call it as drain characteristic okay okay so now let me draw so here first characteristic is vgs is positive or negative
Positive.
the positive means both are positive so it's come in the first quadrant okay so this is id this is vgs so the characteristics will be like this so as vgs increases id increase okay so the voltage which is used to start the conduction we call it as threshold voltage so this is we can call it as vgsn or vtn n channel కాబట్టి n vtn n channel threshold voltage vtn okay the next one is if you draw the output characteristic So this is ID. This is VDS. VDS. Okay. So, and when it VGS is equal to 0, the current is almost 0. So this is for 0. When it is applied 1, 2, 3, 4 like this. So this is 0 volts, 1 volt, 2 volt, 3, 4. So these 0, 1, 2, 3, 4 are the VGS voltages. Okay, this is a transfer characteristics. This is a drain characteristic. Transfer characteristic and drain characteristic.
Sir,
Yes.
sir, by increasing VGS and increasing VDS, we can get current. We can also get current, no, sir.
Sorry, sir. Come again.
Sir, increasing VGS and decreasing VDS also we get current, no, sir.
Some disturbance is coming. What you are increasing? What you are decreasing? VGS is increasing.
VDS is decreasing. VDS is decreasing.
Okay, VDS decreasing.
VGS increasing, sir.
VGS increasing. Okay, then what you are saying?
Sir, current we will get current, no, sir. So
You will get current, but that is the current will be decreased. No, less current you will get. See, from the characteristic, if you take this VGS equal to 4, let us say. Okay, so you are decreasing the VDS in this direction. So see the current, it is coming down, right?
Yes, sir.
So if we increase the VGS and decrease VDS, current will decrease. If you make VDS is equal to 0, the ID completely becomes 0.
Oh.
If we make if VDS is completely 0, if you make it, and ID also 0, this is the origin point, right?
Okay. Sir, I thought we will get negative current.
No. How it get negative current? If you made VDS equal to 0, if you made VDS equal to 0, so means you are not applying anything. If you are not applying anything, though you are applying VGS equal to positive, okay, channel is created. So, but the current is what you can say, the VGS output is not attracting the electrons. It's not attracting electrons, so the current will not generate and it will become 0. But practically, if you make this also 0, if you make VDS is equal to 0, because of the internal repulsion of this electron, all are electrons only, right? So this is the source region is N, and the drain region is N, and the channel also N. So because of internal repulsion, maybe some positive current, so 0.1 or 0.2 current may be generated, but that is not negative. That's not negative. How we will not get the negative current? The current, so electrons are moving from source to drain. Is it right? So if we make our VDS is equal to 0, this drain voltage is not attracting the electrons, so the electrons are not coming out of the device. So there is no current, but maybe some internal repulsion, internal repulsion. There is because something will be generated. So that is also positive, not negative. Clear? Any other queries? Any other? Okay. So draw the characteristics, and we will move to the next. So this is the what we call N-channel depletion MOSFET. Can you draw the P-channel enhancement MOSFET, the characteristics? P-channel. For P-channel enhancement MOSFET, the circuit will be like this. Two diffusions will be diffused. This is the metal to make a contact. This is the gate area. This is source, gate, drain. This is P plus. This is P plus and substrate. Okay, so to create a channel, so this is P plus and P plus. So to create a channel, we should attract positive holes towards the channel. To attract the positive, holes, we should apply the negative voltage here. Voltage will be negative. So then only the holes will come and placed over here. Okay, and now in order to attract the holes, you have to apply the negative voltage here. Negative voltage here applies. So then only it will attract the holes and it will come out from the device. Okay. So it's come out on the device. So the characteristics will be so like this. So this is VGS negative direction. This is ID. Okay, as VGS is keep on decreasing from 0, so the current will increase in the positive direction. Okay, while keeping VDS is constant. This is transfer characteristic curve, and the drain characteristic curve is this is ID, this is VDS. Okay, so here VDS is also negative. Yeah, VDS is also negative. Sorry, the VGS is negative means we should not go like this. So this is negative VDS and ID. Yes, the current will be, so suppose if it is decreasing from 0, so from 0, -1, -2, -3, -4, so the current will increase. So this is for 0, -1, -2, -3, -4, -5 like this. So -5, -4, -3, -2, -1, 0. So these are the transfer characteristic and drain characteristics for each channel enhancement MOSFET. You will get the characteristics like this. Okay, the next take heading uh, depletion MOSFET. MOSFET or depletion enhancement MOSFET or MOSFET. Okay, next topic is depletion MOSFET or depletion enhancement MOSFET or depletion DE MOSFET. So in this we are seeing N channel. Okay, so here the circuit is this is substrate. Okay, so this is this N channel, no? So N plus region, this is P substrate. Okay, so and this is metals to take the leads out, and this is also metal. Okay, so this is gate and source, drain, gate, drain. So this is what depletion MOSFET here, but the difference between this enhancement and depletion MOSFET is difference between enhancement and MOSFET. It consists of channel. Okay, so it consists of a channel. So like this, we have the channel already. Ready-made channel is there for depletion MOSFET. But whereas an enhancement MOSFET, there is no channel. There is no channel for enhancement MOSFET. So that channel we have to create manually by applying that proper voltage, the gate voltage. But there is no question in depletion MOSFET and what should voltage we need to apply. Whether we should apply the positive or negative. There is no question. But because channel is already created and that is ready available, it is already available in the channel. When they are fabricated itself, they provided some space for the channel. Okay, but enhancement MOSFET, there is no channel, but depletion, the channel is there. So because of this reason, there is no restriction for the gate voltage. We have to apply only the positive or we have to apply only the negative. There are no restrictions for the gate voltage. It's clear. So this is only the difference between the depletion MOSFET and enhancement MOSFET. And that's what I told So this is also named as the depletion enhancement MOSFET or DE MOSFET. I will tell you why it is named as a depletion enhancement MOSFET. Okay, so this is the construction. Now I will tell you that, and by taking some differences between. So please note down the circuit, and I will tell you that I will explain again the enhancement MOSFET and the depletion MOSFET, and I will compare both the operations, and I will insert one table. So please note down this circuit. Is over. The circuit is over.
Yes, sir.
Okay. So now see, this is cases, different cases we are going to see, and here MOSFET, and here MOSFET. Okay, so the case one, first case is VGS equal to 0, VDS equal to 0. What happened? VGS equal to 0, VDS equal to 0. What happens? Let us see. Now what happens if you apply VDS equal to 0, VDS equal to 0 in MOSFET? What happened?
Channel doesn't exist.
Okay, no channel. Very good. So what?
ID equals
Current.
Yeah, ID equal to 0. Very good. Now come to the D MOSFET. Now what happened? What happened? D MOSFET lo em avutundi, VGS equal 0, VDS equal 0. Is channel exist in this D MOSFET? Is channel exist or not?
Yes, sir.
yes, sir.
Yeah, channel exists. Why? Because that is ready-made available in this the chip itself, the transit itself, it is available. Here we are not doing anything for the creation of the channel. So the channel creation, it doesn't depends on the type of voltage that you are applying. Okay, so the channel depends on the type of voltage you apply in the MOSFET. Why? Because there is no a ready-made channel in MOSFET. So manually we have to create it. So the channel will be depends on the whether you are applying the positive voltage or gate voltage, negative voltage. That depends on the gate voltage. But the DE MOSFET, so channel is already available. So it doesn't depends on any other parameters. Channel always exists. Channel always exists. Okay. Okay, channel exists. What about ID current or what? What about ID current?
0.
0. Why? Why drain
VDS
current
is
channel
0.
exists? No.
VDS.
Yeah,
VDS
exactly.
0.
VDS is equal to 0. Channel is exist, but VDS is equal to 0, so ID equal to 0. Right. The next case is VGS greater than 0. Greater than 0 means what? That is positive. Okay, VDS also greater than 0. So means both are increasing. VGS positive direction increase avutundi, VDS also increasing in positive direction. What happened in an channel? ఏమవుతుంది అన్ ఛానల్ ఏమవుతుంది? ఈ MOSFET ఏమవుతుంది?
Channel exists.
Okay, channel exist. So channel exists. Then what about the drain current?
ID enhanced by VGS and VDS.
ID Sir, ID?
ID is function of VGS and VDS.
Yeah, very good. VGS, comma, VDS. So it both are increasing. So ID also increase. Okay. So increases. Okay, fine. Now come here. Now see. D MOSFET. You see the circuit and tell me.
Channel exists.
Sorry. Channel exist. Okay, that is channel exist.
ID is function of VDS.
Okay. That's it. ID.
Sir,
Sorry.
sir, only VDS.
Uh, only
Sir, it is
VDS.
only function. Yeah, it doesn't depend on VGS also.
Why it doesn't depends on VGS? So now the question rises here. It depends on VGS also. Why? Because now let us see. Suppose this is N, so now we are taking N channel. Okay. So P substrate. What are the majority charge carriers here? Majority charge carriers are holes. Am I right? Majority charge carriers. What are the minority charge carriers? Minority charge carrier electrons like this. Okay, electrons. So now if you apply the positive voltage, like you're applying the positive voltage like this. Okay, so VGS is increased 0 means greater than 0 and positive voltage. Okay, you're applying the positive voltage. So these positive voltage will attract. These positive voltage will attract. What it will attract? attract అవుతుంది electrons attract అవుతుంది. Electrons అంటే ఇప్పుడు ఆల్రెడీ మీ దగ్గర ఛానల్ క్రియేట్ ఉంది జనరల్. ఓకే, let us assume that the channel consists of 100 electrons. Let us assume that the channel consists of 100 electrons. That channel something is there. So now in addition for that 100 electrons, VGS is attracting that negative charge carriers in the P substrate. Understood? So because of VGS, let us assume that 5 electrons are attracted. So now what are the total number of charge carriers in the channel? 105. Now tell me, so is ID depends on VGS or not? Just compare. So ID due to 100 charge carriers, ID due to 105 charge carriers, which will be greater?
105.
105. So that 105, how you are getting that 105? Because of VGS or not?
Yes, sir.
So here also ID also function of VGS only, but channel consists of 100. So because of your applying positive charge carrier, okay, so because you are applying the positive charge carriers, so 5 more electrons may attracted and it comes and plays in the channel. So 100 plus 5, let us become 5. So because of 105, the current conduction decreases drastically, so it becomes more when compared to that. Yes or no? Yes. So the channel exists. ID is a function of VGS comma VDS, and ID current increases drastically. Why? Because it is adding another electrons to this. Okay, fine. The next condition is the third condition. If VGS less than 0, VDS greater than 0, what happened? Yes, in this condition, what happens? So VGS less than 0, VDS greater than 0.
Our
MOSFET.
channel exists.
Channel?
Channel doesn't exist.
Yes, channel does not exist. Why? Because we are applying a negative voltage. So, but what you have to apply? You have to apply the positive voltage to exist the channel. Okay, so it doesn't exist. So if the channel doesn't exist, though VDS is greater than 0, whatever, but there is no path. Yes or no? So the channel is doesn't exist means though VDS is greater than 0, ID equal to 0. Why? Because there is no channel. Am I right? So same thing you tell me for DE MOSFET. If VGS is less than 0, VDS is greater than 0.
Exists.
Yeah, channel exists. Okay, fine. What about ID current?
ID is function of VDS.
Uh,
ID is function of VDS.
function of VDS only. Am I right? Or VGS comma VDS.
VGS also, sir.
VDS comma VGS, right? Now, what about ID current? Increase or decrease? See, you are applying, so this D MOSFET, you are applying the negative voltage here. Okay, you are applying the negative voltage. So negative voltage you are applying. Now see that how it will be. Tell me whether the current increase or decrease. A simple boss.
Decrease.
Decrease, right? Exactly. So why? Because here 100 electrons are there. Assume that. What we are doing now?
Covalent bond.
You are applying that negative polarity, negative charge current. Negative charge current if 100 electrons repel with attracted waving. So you are at the negative polarity, negative battery, and electrons are accumulated at the inverse layer. So these 100 electrons will repel by the negative battery and it will away from the channel. So this electron will come away from here. At the same time, this negative polar of the battery attracts the majority charge carriers of the P substrate, right? What are the majority charge carriers of the P substrate? Holes, and the holes will come and place in the channel. So if it is electrons are away from the, it is coming out of the channel and the holes are entering the channel. So let us assume that 100 electrons, 10 electrons, by, for example, 10 electrons are coming out from the channel, and the 10 holes are entering the channel. Okay, so these 10 holes are participating with the covalent bond with the 10 other electrons, and what will be the resultant electrons in the channel? 10 are already out, 10 are participating in the covalent bond, and what are the resultant? So you will be having only 80 electrons in the channel. Yes or no? So in the out of 100, 10 already left the channel, and the remain next another 10 electrons are participating the bonding. And what are the number of free charge carriers, free electrons? There are 80. So the current due to 100 is more, the current due to 80 is less. So therefore the current here the ID current decreases here. Am I right? ID current decreases. Yes or no?
Yes, sir.
Yeah. So the next one is one more case. If VGS equal to 0, VDS greater than 0. What happened now? What happened? MOSFET. If we are applying VGS equal to 0,
Channel doesn't exist.
channel doesn't exist. Okay. What about ID current?
0.
0.
ID current 0. Why? Because so there is no channel, there is no current. Clear. Now come here. What about this? What about this? Channel exists.
Channel exists.
Yeah, channel
Exist.
exists. Okay. What about drain current? Drain current increase or decrease?
Increases.
Increases.
Increases, right? Okay. Now you see there are the 4 cases. Now observe that. So MOSFET already is seen, right? MOSFET already is seen. So you draw the characteristics also. Leave it. Now come back to the depletion MOSFET. So in this case, drain current is 0. In this case, current drastically increase. In this case, current decrease. In this case, current increase. Okay. అంటే మీకు MOSFET లో డిప్లీషన్ MOSFET లో డిప్లీషన్ ఎన్హాన్స్మెంట్ MOSFET లో కరెంట్ ఇంక్రీజ్ అవుతుంది, డ్రాస్టికల్ ఇంక్రీజ్ అవుతుంది, డిక్రీజ్ అవుతుంది, 0 అవుతుంది. Did you understand this? Okay. So this I will draw the characteristics. So by taking this condition, now just listen this. This is the transfer characteristics. Okay, so transfer characteristics. This is ID. Okay, so 0. This is plus VGS. This is minus VGS. Now go back. What is the first condition? VGS equal 0. So this already drawn these characteristics. Now let us leave about this. Now let us come here. If VGS 0, VDS 0 at E point. So VGS 0 at this is the point. What is the current? What is the current?
0.
Sorry? 0. Okay, 0. Leave it. Now coming to VGS greater than 0. VGS is greater than 0. Okay, so ID current is ఏమవుతుంది? It drastically increases. Okay, so VGS greater than 0 means positive. So positive reaction లో drastically increase అవుతుంది. Okay, so drastically అంటే ఇక్కడికి వస్తుంది. For example, let us say drastically గా. Next వచ్చేసి VGS less than 0 అంటే నెగిటివ్. Sir, no. So negative. So negative means what? Sorry, in the so negative వచ్చేసి so negative direction the current వచ్చేసి ఏమవుతుంది? The current is what is this? Decreases. So for the negative direction is current decreases, and if it is 0, VGS is 0, so ID increases. Yes or no? So VGS 0 ఉన్నప్పుడు VGS is 0, so ID increases. So the graph will be like this. సో VGS లెస్ దాన్ ఉన్నప్పుడు కరెంట్ డిక్రీజ్ అవుతుంది, VGS పాజిటివ్ ఉన్నప్పుడు డ్రాస్టికల్గా ఇంక్రీజ్ అవుతుంది, VGS జీరో ఉన్నప్పుడు కరెంట్ ఇంక్రీజ్ అంటే ఇక్కడ దాకా వస్తుంది. దిస్ ఈస్ ది ట్రాన్స్ఫర్ క్యారెక్టరిస్టిక్ ఆఫ్ కర్వ్. Okay, so this you can write, this is if you observe that this is enhancement MOSFET characteristics. Enhancement MOSFET characteristic, am I right? Go back and you can see this is enhancement transfer characteristic, right? Okay, so this part is enhancement MOSFET and this part is only depletion, so together we call it as depletion enhancement MOSFET. So that is the reason we are calling depletion enhancement MOSFET. So the depletion MOSFET can be used as the depletion and enhancement, but enhancement MOSFET can be used as only enhancement mode. So this is the advantage of the depletion MOSFET. So the depletion MOSFET can be used as the enhancement MOSFET and the depletion MOSFET. Okay, whereas E MOSFET can be act as only E MOSFET. It's clear? So now coming to the next version, the drain characteristics. The drain characteristics. Okay, yeah. So coming to the drain. Drain undamma ikkada. So drain is zero, current is zero. So there is no current. Yes, the VDS is zero ante ikkada current is zero. So okay, fine. This side. Next vachesedi the drain all are increasing. So now let us come to VGS equal 0 nappudu em ostundi. This is 0 volts. Okay, so this is 0, some current you are getting. If VGS is greater than 0, current em otundi drastically increase also. So if apply, if it is positive, the current will be more. VGS is more. This is plus. This is plus 2, and even if you apply more voltage here, you will get the more current. So if you apply the VGS less than 0, current em avutundi decrease. This is minus 1 voltage, this is minus 2 voltage, this is minus 3 voltage. గ్రాఫ్లు మీరు స్ట్రైట్గా డ్రా చేసుకున్నాం. ఇది VDS and this is ID. Okay, so in this one again, this is E MOSFET and this is D MOSFET, together DE MOSFET. మీకు E MOSFET కి దగ్గర వచ్చింది, back and see 0 1 2 3 4 positive. So 0 plus 1 plus 2 plus 3, that is E MOSFET, and this is D MOSFET, together DE MOSFET. So depletion MOSFET can be used as depletion and enhancement. So this is the advantage of depletion, but most of the, so in the fabrication purpose we'll be using only E MOSFET. We will not use D MOSFET in the fabrication. Why? Because E MOSFET there is no channel. So there is no channel means there is no need of providing space for the channel. There is no need of providing space for the channel. So if there is no space, I mean there is no need of allotting some area for the space, and the area can be decreased, area can be saved, and the area of size of the transistor will be less, very narrow. And whereas coming to the depletion region, so channel is created, channel is available in the structure. Okay, so anyway channel is there, so means it occupies some more area, right? So comparing the E MOSFET, D MOSFET occupies the more area compared to E MOSFET. Okay, but E MOSFET, if there is no channel, but manually you can create it. You can get the current. Okay, so but the current, the drain current, you can make it flow. So flow from the source, drain to source. Okay, so meeku channel lenanta maatrana meeku current time 0 ayipotledu. So manually you can do it. Okay, but so that in the what is the important parameter? It saves your space. So for that reason, E MOSFET always used in fabrication purpose. Always used in the fabrication purpose. And whereas the depletion MOSFET, so it used in some kind of amplifiers and switches, but that always used in the this one. Okay, so this is today's class. Any queries? Any queries?
No, sir.
Okay, so the next class we'll discuss CMOS static logic, and we'll do some problems. CMOS static class will take only just 20 minutes of time, and we'll solve some problems. By next class we'll so tomorrow we have no, so by tomorrow I will close this third module, and the Saturday also I'm going to take the class in the first and second hours. I mean I'm planned to take, and till now I didn't ask the GS madam, but I will ask, and I will take it on Saturday. Max I will take, otherwise so madam will take, so that not at confirm. If it is EDCA, so by Saturday I will start fourth module. Okay, the third model is, see, everything is depletion, enhancement, or JFET. If we take, only depends on the VGs and VDS. So only please concentrate on the conditions. So if you apply this condition, what happens? This condition, what happens? That's why how to take it. So like this, what I told, that table, no. So the table is prepared for N channel JFET, P channel JFET, N channel MOSFET, and P channel MOSFET. So like that. So 6 types we know. So you can create that thing. So therefore you will get some clarity. Okay, so and as a complete model, this is all the complete module. Only single table, if you prepare, if you prepare that single table, that it explains the entire module. So that's what this very easiest module in the EDCA course. So definitely you can score 20 marks in external without lose any marks, and the numericals also, that depends on only single formula that I will tell you. Okay, so that is as a Shockley current equation, ID equal to IDSS into 1 minus VGS by VP whole square, that I will tell you. Anyway, will in the next class we'll solve some problems. And the most important thing is, once again I'm telling you, if you join before 10:35 PM only, I will allow you people to the class. Okay, so so many people are messaging me and calling me to my mobile, but I'm not responding for them. Okay, so even if you admit initially, and if you unfortunately exit from the class, and due to some technical issues or something like that, if it exists, those cases I will consider. If you log in before 10:35 by mistake or network issues, if you exit, that I will consider you people. Okay, who are those who are not entering before 10:35, I will not allow. Okay, so today's class strength is only I think how many are there in the class? 33 members are there. Okay, so I will take 33 only. The remaining 27 will be absent. There is no question in that. ఓకే, సో మీరంతా తీరిగ్గా మీ అన్ని పనులు వేసుకొని 10:35, 10:40, 10:50, 11:30కి వస్తారంటే నేను అలౌ చేయను. ఓకే, సో 27 మెంబర్స్ నేను ఆబ్సెంట్ చేస్తున్నాను ఈరోజు. రైట్, సో నెక్స్ట్ రేపైనా సరే 10:35 షార్ప్, 10:35 ఉంటేనే క్లాస్కి రండి, లేదంటే నీ నాట్ లాగిన్. ఓకే, సిఆర్స్ ప్లీజ్ ఇన్ఫార్మ్ టు యువర్ ఫ్రెండ్స్ ఆల్సో. నేను ఎవరినైతే ఈరోజు అడ్మిట్ చేయలేదు, సో అందరూ మీకు వాళ్ళు లాబీలోనే వెయిట్ చేస్తున్నారు.